Okay, so this is 7.1, systems of linear equations and two variables. And first we're taking a look at solutions. So this is problem 2. So I mean, what the heck's going on? Well, it's similar to what you did with your first introduction to solving equations in general. So maybe to the side here, I can, like, they would give you an equation, 2x plus 1 equals 3, and they would say, here's a potential solution. Try it and see if it works, right? So you would plug 1 into here, and you get 2 times 1 plus 1 equals 3. And then 2 times 1 is 2, plus 1 equals 3, and then 3 equals 3. So yeah, it's a solution. So what you're going to do in the beginning is just checking to see whether something works. And then later we'll show you methods for actually solving the equation. So here we're not solving the equation, we're just checking a solution, and potentially you don't even know how to get to the solution just yet. Okay? So that's kind of what we're after here in this first section. They give us a point, -3.5, and our system now is comprised of 2 equations and 2 unknowns. So you may hear teachers say 2 equations, 2 unknowns, 3 equations, 3 unknowns. Any of those scenarios are fair game for finding solutions. Okay, so to determine if there's a solution, we plug the ordered pair into each equation, and each equation has to result in a true statement for it to be a solution to the system. Okay, so we'll try first putting it into 9x plus 7y equals 8. So I'll have 9 times, and remember this is my x, this is my y. So 9 times -3 plus 7 times 5 equals 8. 9 times -3 is -27, plus 7 times 5 is 35, equals 8. And then -27 plus 35, of course, is 8. Okay, so we get a true statement there. I need to still check the other one, right? So here I have 8 times -3 minus 9 times 5 equals -69. So I have -24 minus 45, on the other side -69. And if you subtract these, certainly you get -69 equals -69, so that's a true statement. And because both are true, this tells me that -3, 5 is a solution. Okay, so how then do I find a particular ordered pair which is a solution to my equation? How do I go about finding this? Is it like what I did over here in linear equations? Do I just add -1 to both sides, divide by 2? Well, not really. There's 2 methods that we're going to be using. The first method is called the substitution method. You'll still use all your properties of equations that you learned earlier. So you can add something to both sides, subtract, etc. Let's just get in there and take a look. Okay, so number 8, we're given the system 2x minus 3y equals -13, and then the equation y equals 2x plus 7. So your first step is to solve one of the equations for one of the unknowns. Okay. So I'll solve that second equation. It's already solved, so I really don't have any work. I'm just going to notate this is what I have. Okay, secondly, substitute this expression into the unused equation. So in particular, you need to be careful not to substitute it back into itself. What you'll end up with is a true statement. In other words, and we'll talk about this later, you'll have infinite solutions to that system. So you don't want to set this into here, you want to set it back into here, this unused equation. So sub your expression from step 1 into the unused equation. Okay. So that's what you do. Plugging it into here, wherever you see a y, you're going to put parentheses 2x plus 7. So I'll have 2x minus 3 times 2x plus 7 equals negative 13. And then you're working with a linear equation and one unknown, and we know how to solve this from previous classes. So 2x minus 6x minus 7 is negative 13. Then we have negative 4x minus 7 is negative 13. Add 7 to both sides, so I have negative 4x equals negative 6. What did I make? I made a mistake somewhere. Sort of checking my notes, I'm sorry. Oh, I didn't distribute here, sorry about that. So this should be 21. And then you'll have negative 4x equals 21 minus 13, so 7, 8. And then divide both sides by negative 4, so x is negative 2. Okay, once you get this guy, you're going to substitute it back into either equation that has 2 unknowns, but it's better to use the equation from step 1 because it's already worked out. So I'll just say substitute our value from step 2 into the equation from step 1. Okay, so this it's sometimes hard to remember to do that. And if you, yeah, what?
Find out how much money for that.
Okay.
I'm serious. That is very good investment, and they sold to somebody else. People does the next day.
Well, yeah, but it could be like $300,000, and there's just no way.
It won't be that much. And buying from her, we know her, and she might even give us a break on it.
All right, I'll ask her.
Because she knows we're not going to build it.
All right.
And that's the way she would like it to be. So you find out.
Okay. So anyways, you take the...
The option is to find out how much it would be to buy the first 100 feet back.
Right.
Along the edge.
Okay, I'll ask. Okay, so 2 times negative 2, so you're plugging x back into this equation here. So sorry about that. A lot going on today. Substitute this into the first equation, so you'll have y equals 2 times negative 2 plus 7. So y equals negative 4 plus 7, which is 3. So the ordered pair then, and you know, in the previous problem they just give it to us. Now we can figure out what the ordered pair is without that, without the book helping us. And in particular here, the ordered pair is negative 2, 3, which is the solution to this system. You can always check. Usually I won't check. But, you can check it in the same way we checked in problem 2 here. Okay, so now we just want to look at a couple more, and then we have another method for solving these systems. Anyways, so here's number 14, and my system, 2x plus 5y is 1, and then my other equation, negative x plus 6y is 8. So in first step, solve one equation and one unknown. Generally what you'll do is look for the one that doesn't have a coefficient on it. So this guy has a negative in front of it, but that's not gonna, the problem is causing fractions. You don't want any fractions. So you're gonna work probably with this equation here. Sometimes there's no way around it. You have to have fractions, but if you can avoid it, avoid it. So that's why I'm solving for the x. So anyways, I'm going to move the negative x to the other side to get x equals 6y, and then move the 8 to the other side, minus 8. And now I'm going to take this guy and substitute it into the unused equation. Okay, so that'll be this guy right here. And then I'll have 2 times 6y minus 8 plus 5y is 1. Then I need to distribute. So I'll have 12y minus 16 plus 5y is 1. Combine like terms. So 17y minus 16 equals 1. And then solve for y. So 17y equals 17. And finally y is 1. Right? Lastly then, back substitute it. So step 3, I'm plugging this number 1 into this equation because it's so nice. Again, you can use either one of these, but you just have more work to do. Okay, so I'm just going to use this guy. X equals 6 times y, which is 1, minus 8. So x is 6 minus 8. In other words, x is negative 2. So our ordered pair solution this time, negative 2, comma 1. All right, let's look at one where we have some fractions to deal with. So this is number 18. Y equals negative 1/2 x plus 2. And then y equals 3/4 x plus 7. So step 1, we want to solve one of the equations for one of the unknowns. And we've already done that, right? Both equations are solved for y. You can pick whichever one you want. I'll just take the first one I see. And then secondly, substitute this expression into the unused equation. Okay, so to do that, ultimately all you need to do is set the two equations equal to each other, so to speak. I'll substitute in this for y on the left-hand side, and you get negative 1/2 x plus 2 equals 3/4 x plus 7. And then I like to get rid of fractions. So I'm going to multiply by something that's divisible by 4 and 2. Particularly, I want something that's small, right? So 4 is divisible by 4 and 2. So I'll multiply both sides by 4. Right. On the left-hand side, 4 times negative 1/2 is negative 2. 4 times 2 is 8. On the right-hand side, 4 times 3/4 x is 3x. And then 4 times 7 is 28. Okay. So I'm going to move the 2x to the other side, end up with 5x. Move the 28 to the other side, you get negative 20. And finally solve for x. So x will be negative 4. Right. Substitute this now back into the equation from step 1. You get y is negative 1/2 times negative 4 plus 2. Negative times a negative is positive. 1/2 times 4 is 2. And at the end, we get the solution, a negative 4, comma 4. Okay, so that's our first method for solving systems, the substitution method. The next method we want to look at is called the addition method. And I'll be expecting you to know how to do both methods for the test. So looking at 24, here's my system, 2x minus 7y equals 2, and then 3x plus y is negative 20. So the deal here is you want to add column-wise, and you're hoping for a cancellation of one of the variables. Okay, so 2x plus 3x is 5x, negative 7y plus y is negative 6y. So you don't get a cancellation here. So what you want to do is either multiply the top one or the bottom one, or both, by a non-zero constant to produce a cancellation. Okay, so it seems like if I multiply the bottom guy by 7, I'll get just that. So 7 times 3x is 21x, 7 times y is 7y, and then 7 times negative 20 is negative 140. And then scan again. So if I scan, I see, all right, the y's are going to cancel, and that'll be a good thing. Okay, so I have 23x equals negative 138. Okay. If you divide both sides by 23, playing a calculator, you get x is negative 6. Now you can take this value and plug it back into any equation that has both unknowns. Okay, so you got 4 choices. I usually just take the first one I see, the first equation here. So 2 times negative, and it won't make a difference. Whatever equation you use, as long as it has both unknowns, you're going to get your answer. Okay, so here we have negative 12 minus 7y is 2. Add the 12 to the other side. Divide by 7, negative 7, and you get your solution. Okay, so the answer, negative 6, negative 2. Let's look at another problem 30. So our system, 5x is 6y plus 40, and then 2y is 8 minus 3x. Okay. The first thing I want to do is to get both equations into a standard form, and this is considered the standard form here. Okay. So I'm going to move the 6y to the other side on the first equation, so 5x minus 6y is 40. On this equation, I'll add the 3x to the other side, so you get 3x plus 2y equals 8. The deal is you want to get all the variables lined up, so it becomes a little easier to work with your addition method. Okay, so I scan. I'm not seeing any cancellations, but if I multiply the bottom guy by 3, then I think I'll get something, right? So I'll have in the top 5x minus 6y is 40, and in the bottom I'm getting 9x plus 6y equals 24. Okay. And now I can go ahead and add column-wise. The y's will cancel out. I have 14x equals 64. And then divide both sides by 14. And I get x equals 64/14, which can be reduced into 32/7. Okay, I'm going to take this guy now and plop them back into any of the unused equation, or any of these equations, so long as they have 2 variables. You can use any of them. Okay, so I'm just going to go back to, I don't know, it's not going to make much difference. So let's use this guy right here. Okay. So I have 5 times 32/7 minus 6y is 40. Multiplying here, I believe we get 1/67 minus 6y. And I'm going to have to move this to the other side, so I'm just going to get it out of the way and get a common denominator here. I need a 7 in the denominator, so multiply top and bottom by 7. You get 280 over 7. I'm sorry, yeah, 280 over 7. And then subtract the 1/67 to the other side. And so 280 minus 160, so go to 1/27. And then multiply both sides by negative 1/6. Okay. So over here, 6 will go into 120 20 times, and you'll just be left with negative 27. And on the left-hand side, you'll just have a y. So our solution this time, 32/7, comma, negative 27. Okay. So that one wasn't very pretty, ended up with some fractions. Okay, the next section then we're dealing with what are unusual solution sets. And the best way to, I think, swallow this pill, so to speak, is to think geometrically. Okay, so 1, 2, 3, unusual solution sets. So geometrically speaking, when you have a system of equations like we've been dealing with, each equation represents a line in the plane. Okay? So there's going to be 3 cases. And the cases we've been looking at have been this kind of case. There's one solution because the lines intersect at one place. Okay? So in the cases we've been looking at, this is how they would look if we were to graph them. There's 2 other cases, though. There can be these cases when your system is comprised of 2 parallel lines. You have 2 parallel lines, they'll never hit each other, so you will have no solutions, 0 solutions. Okay. The third case is the infinite solution case. You may have heard me say you don't want, when you're doing the substitution method, to put the equation right back into itself, because you'd end up with infinite solutions. Okay, and that's this case here, where both equations in the system are the same. Okay, you have infinite solutions. Okay. So these are the unusual solution sets over here. These 2 right here that we haven't yet looked at. It turns out they're pretty simple algebraically. The big red flag is that the variables will cancel out. You'll just have a statement resulting like 5 equals 5 or 2 equals 7 or something like that. So let's take a look. The first case is the infinite solution case. And the resulting statement will be, for example, something like 7 equals 7. Okay? And that will be your red flag, and you'll say, oh, that's infinite solution case. So let's look at 38. Sometimes you could tell just by looking at the system, but sometimes you can't. So if you could study this in depth, and you kind of see patterns evolving, like if you look at this equation and this equation is just a multiple of this equation. It seems like that's a good way to say, well, that means there's infinite solutions. So anyways, if you multiply the second one by 2, you're going to get a nice cancellation. So at this point, we don't overthink it. We're not really looking for patterns. We're kind of just figuring things out. In particular, we want to multiply by -2, right? That way there will be a cancellation. So let me go through there and change those. So 4x minus 4x is 0, -2y plus 2y is 0. And on the other side, we also have 0. Okay? So this is the characteristic of infinite solutions. The variables will cancel out. You'll be left with some statement. In this case, it's a true statement. And when it's a true statement like this, it'll tell you it's infinite solutions. Okay? So you can write infinite solutions for me. That's fine. The book will have set builder notation, and the way they write it is the solution is the set of all points x comma y such that x and y fulfill one of these equations. Okay, you can pick either equation because they're technically the same. Okay, so we can say 4x such that 4x minus 2y is equal to 2, and that would be your answer. Of course, you could also say or the set of all points x, y such that 2x minus y equals 1. Okay, those would be equivalent answers. And if you don't care that much, you can just write infinite solutions. Okay. All right, so let's look at 32. We have the set 6x plus 2y equals 7, and then also y equals 2 minus 3x. Okay. So this time it's kind of set up for the substitutions method because one of the equations is solved. Okay. So I'm going to take this and then plop it back into the unused equation. So step 2, I have 6x plus 2 times 2 minus 3x equals 7. And then I could solve this thing by distributing here. So 6x plus 4 minus 6x is 7. And then 6x minus 6x is 0, so you end up with 4 equals 7. Okay, this is the other unusual solution case. This is the case where the lines are actually parallel if you were to plot them in the plane. Okay, so when the variables cancel and you end up with a false statement, that tells you that there are no solutions. And if you want to use our set notation, you could write the null symbol, which is equivalent to the empty set. So the set with nothing in it. Okay. Okay. So part B then, the no solution case we just looked at. And for example, you'll end with a false statement, like we just saw, 4 equals 7, that's false. And so you'll write no solutions or the null set symbol. Okay. Okay, so applications. On the test, I'll be focusing on the motion application. So section 4 then, applications. And in particular, we need the motion formula memorized. So motion, we're going to know distance equals rate times time. So I was traveling 50 miles per hour for 2 hours. How far did I travel? Well, you traveled 100 miles. How do you figure that out? Well, you multiply rate times time. Okay, these formulas come in other forms, obviously. You can solve for R, and you get d over t. You can also solve for t, and you get d over r. But this, as long as you know that, you can go ahead and get the other formulas. I gotta get my book so we can figure out what the question's saying. Okay. So let's take a look. 7, 1, number 62. When a plane flies with the wind, it can travel 4,200 miles. So let me write this up. This is 62. Plane with the wind. When a plane flies with the wind, it could travel 4,200 miles in 6 hours. When the plane flies in the opposite direction against the wind, it takes 7 hours to fly the same distance. Okay. Find the average velocity of the plane in still air and the average velocity of the wind. So let's define x to be the average velocity of the plane. In still air. And then y will be the velocity of the wind. Okay, so you can make a table to help yourself out. What we're trying to do, though, is to produce a system of equations, right, based off this formula. So each equation will be based off this. So you'll have, in particular, we can almost figure it out right now. The distance is 4,200. So we're building a system of equations. And that equals rate times time. So the rate of the plane when it's going with the wind will be x, the rate of the plane, plus y, the rate of the wind. Okay? And then times t, and t when it's going with the wind was 6 hours. Okay? When it's going against the wind, the overall rate is going to be x minus y. So you think of it like the wind is taking away from the speed of the plane. If you went outside when it was really windy, you'd go a lot faster, going with the wind than you could running against the wind. You literally feel it as you're running. Right? So those will end up being our system. let's rewrite them so they're in a standard form. So I have 6x plus 6y equals 4,200, and then 7x plus minus 7y equals 4,200. You can simplify these equations just as you would simplify any equation. You can multiply through this equation on both sides by 1/6. In other words, divide everything by 6. Right? So you would get x plus y equals 700. And then if you divide everything through here by 7, you get x minus y equals 600. Right? And then we already have a cancellation set up for us. So x plus x is 2x, y minus y is 0. And then 700 plus 600 is 1,300. And then x is equal to 650. Okay? So what is x? X is the rate of the plane. We still need to figure out the rate of the wind. So you can go back to any equation you have here. Probably the easiest one is this one right here. So you have 650 plus y is 700, and then solve for y. So y must be 50. Okay? Make sure these are reasonable numbers. If you get a plane going 1,000,000 miles per hour or negative 100 miles per hour, you know it's probably wrong. So anyways, the speed of the plane is 650 miles per hour, and the speed of the wind is 50 miles per hour. And that'll do it for 7.1.